Okay.
I'll take the notes.
Okay, you'll take, okay, so you two are. And you might want to exchange your email so that you can coordinate. Okay, that's, I think these guys did a reasonable job last time. So.
You can redirect to me.
Okay. Karthik, can you ask Judith or somebody to check on Zoom whether it's. Oh yeah, that's true. Good. You can tell. Yeah, it's working as it's supposed to work. Finally. So that's just you, I guess. Okay, that's right. So you could hear me, I guess.
Yeah. And you should be able to find the PGDL tutorial with what happened. I don't remember that being.
Yes. What?
Are you sharing this screen?
Yeah.
Which one? I mean, no.
So for example,
We can see it.
yeah. No, I mean it's basically going via Zoom. Right? Yeah, it's going via Zoom, so it'll all be working. Yeah, this is how it worked last time. So it should work. Okay. I don't know whether I'm supposed to continue to wear the mask or not, so I will do crazy things. In the middle, I might wear, and then might take it off, all that stuff. But as Juan said, since I am wearing it, if you feel like you should wear, you know, I mean, you don't need to be. This whole thing is behavioral economics. It basically shows that says the following thing, that if you're waiting at an intersection, waiting for the walk sign to come on because you're a goody two shoes person, and somebody just crosses you and walks without even though the sign says don't walk, you feel as if the powers that we gave you permission also to walk. Okay, so similarly, so we tend to have this kind of irrational behavioral economics. So if you're thinking that I can't wear because nobody else is wearing mask, you should feel because I'm crazy enough. Okay. And I don't know when we'll ever come out of mask. Actually, it's not at all clear to me. I think in Taiwan, Hong Kong, etc., they never got out of it after SARS. So you'll at least get fewer colds. But if you guys can hear me clearly enough, right? I don't sound any more mellifluous. This is basically me, so. Okay, so we will get started, I should remind myself, and I put an alarm too, that actually they have done a pretty rational thing. I don't know why I never realized this. So the class starts at 1:30. If it is a normal class, you would have ended at 2:45, right? That will be 1 hour 15 minutes. And then there's a 15-minute break. Then we start again at 3 o'clock and at 4:30. It really is 2 1 hour 15-minute classes with a 15-minute break in the middle. So you got shortchanged out of 5 minutes last week. Anyway, I never really, I mean, I've done this in the past, but I never realized that there is actually a method to the madness. So, okay. We will try to do that. Okay. So, like I said, we have stabilized. These are the phases that you'll be seeing for the rest of the semester, unless you decide to drop out too. So look around and see who are the people who are going to be in the class. It's a pretty good number, I think. I would have liked even smaller, and much more ready people. But I think since I've done enough of scaling, I didn't physically remove anybody. Okay, so don't write to your senators. They just decided that it may not be worth it. So there are 44, I said 9 PhDs, 9 undergrads, 12 masters in computer science, 9 masters in robotics and automation, 3 MCAs, and then a couple more. That's basically the type of class we have. I'm assuming that only that people with the background in intro to AI stayed. So if you are not one of them and you decided to stay, then you are completely responsible. I will feel comfortable dropping things, jargon that we have discussed in intro to AI. And if it doesn't make sense to you, write it down, put a circle around it and look it up. Okay. So grading, etc. We're still finalizing this, but it's become better now. I know that it says, smaller class with people who are interested, who have the background. So the main things we will be doing would be some homeworks. The first one will actually has already been put up on the piazza. I'll be discussing the stuff related to that today, which is basically planning domain description language, and how do you write planning domains. So that's the first one, and we'll see more of those as the semester goes on. And some of them might need coding. This particular one actually doesn't need coding at all. It's just writing the domain in a particular fashion and then seeing whether or not the domain was correctly written by checking whether the planner that is already inbuilt into a particular online editor that you will be using, whether it actually solves and gets you the plan. If it doesn't get the plan, presumably you wrote the wrong domain model. This is sort of like writing the program, of the domain program, not the full planner. So you're sort of giving, those of you who have background in Prolog, you can think of it as essentially a declarative specification of the dynamics of the domain. Okay. And then there is a search strategy. There are different search strategies that you use that will work on that declarative specification of the dynamics of the domain and generate plans. There's a whole entire world out there. I will start talking a little about that. Again, once again, it's not surprising that in the AI, pretty much every topic can be an entire course. And it continues here that every little topic that I bring up could be like a half a course. But I will do something and move on to the next topic. And then you can at least, actually that these things exist. So that would be a useful part of the knowledge you get. Okay. I am now more considering more seriously a final project. And I will tell you, I know many grad classes actually have final projects that people make up themselves. They essentially provide a proposal for the final project, and then actually complete it themselves. In general, it's a very good skill in research, because in research, solving the problem is not the hard part. Deciding what the problem is. Okay, and in fact, coming up with what would be a reasonable thing to do especially in real life where you're actually trying to extend the state of the art and there's a huge number of things that haven't yet been done, which one are you going to pick? That's going to be, the biggest skill people learn in PhD. Okay, essentially, how do you pick the problems? How do you solve them is important, but how do you pick them is probably even more important. And so it's a very, very, very soft skill. Nobody teaches you exactly, and that's why you hope that you will learn it by experience. And in grad classes, we try to do this sometimes. And some of the best class projects will become actually referred conference papers, and some would at least tell you how to do things. Normally, if this had been 100 people class, I wouldn't have thought of doing that because it's not worth it. Because people will just, it's basically you have to have some minimum expectation on the background of the people. Certainly, I'm going to do a little more thinking on this, but we will have a final project very likely. And then there would be credit for participation and readiness. For example, pre-class readings, anything that I ask you to view before the class, you go do that. Participation in piazza, and then of course paper reviews when we get to the point where you start reading papers. Like for example, today you should have read those 2 chapters. I'll assume you did. If you don't, again, it's that class, right? Honestly, if you don't want to learn anything, you don't have to learn anything. That's in general that's true always, but certainly true in that class. And then midterm and our final is what I said. I probably might have at least a midterm, and I'll decide whether or not to have it. Okay, and more likely than not, they will be, unless you give me reasons to believe that I can't even trust grad students. Undergrads might be saying, those are the ones you should trust. You should really trust us. But anyway, I'm hoping that if you decided to hang around in this course, I'm hoping that I can trust you. And by the way, this is a grad class, so I don't want to repeat this, but I do say this in normal classes that I assume everybody is honest and trustworthy, but don't mess with me because I've been here for what, 32 years, and I can send you back. If I find, I have lots of time, I'll make up if I really need to, go over sort of dishonest practices. It's not like I'm going to let it go because I have to do that for the benefit of people who are playing by the rules. Okay, so I'll assume all of you are honest and you follow the rules. That's basically the expectation. But if I do wind up finding a reason that you actually cheated, then it won't be pleasant for you. Okay. Okay. Before I go forward, so the percentages I haven't given yet, but I'll hopefully give more by the next week or something. But again, once in the end, it's a grad class. I'm not going to exactly say 2.37% for opening your mouth on every alternate Friday or some such thing. So it was going to be actually in the end. Even in normal classes, you have a cumulative. That only sort of is a softmax distribution that sort of provides some kind of a probability on what your grade is likely to be. Okay. Everything important in life, unfortunately, is subjective. Quote me on this. It's like because most important things are not. You don't have enough clean cut, 1, 2, 3, 4, 5 things that a machine can interpret and give a mark. So in the end, you have to assume that I am the one who's going to give the grades, but there is going to be, how bad is this guy? Like, if this guy giving A+ to a person who never showed up in the class, then it's very bad situation. So, but in general, I will try to make sure that there will be situations such as some people who are not really ready to do a final project, but they will wind up doing it. They do something that's of a lower quality. I might take higher credit, higher percentage for them for the midterm performance, for example. On the other hand, people who can write paper quality research, then fine. That's if they don't do well in the midterm, that paper will get higher. So we'll do that. I do the for undergrad too, but certainly we'll do it. Any questions on this topic? Yes.
I have a question on the logistics of assignment 1.
Mhm.
So I don't find any due date specified. On the
Yeah, so we just made it today. I mean, so basically, I'm trying to see. First one, I'll try to speak. I mean, first of all, it's supposed to be 1 week. For this one, it should not be more than 1 week.
Okay.
Okay.
Before the next class.
It would be next class, and we will give actual the rules, I mean, the actual instructions as to how do you submit, etc. Okay. I just put this up so that it actually shouldn't take too much time. You know, you basically are writing a couple of the things. It's just to get your heads right. Okay. But this one is approximately 1 week, and the exact date, due date, and the submission instructions will be provided on the outside. Okay. Other questions? Okay. So today, what I'm going to do is actually go into, remember there are different kinds of, depending on the types of problems that you consider, even though they all fall under the canopy of an umbrella of planning, you can differentiate between certain classes of subclasses. Okay, one of which is operator-based or strips or PDDL planning. I will get to that today. Okay, it's not motion planning, but on the way to PDDL planning, we'll talk about MDPs, which are basically atomic version of stochastic planning. I'll talk about them. Okay, so that's what I'm going to do today, and getting to make you think about what's the advantage of thinking of domains in this sort of lifted way as against black box transitions, you know, between states by Axioms. Okay. Before I go forward, are there any questions from last class? Is there any? Actually, let me ask the following thing. Can somebody, for example, a couple of people raise their hands and say, what, if anything, was surprising that you learned last? Yeah.
Just how much of AI planning covers? There's just so many things.
Yeah, that's because I'm a planning guy. And I think the whole point of AI is planning. Yes, you're actually right. That's true, but you know, but that's a good point. But other things, that's a reasonable point. But anything that surprised you? Yes?
I guess symbolic systems are more for us to understand inputs more than like.
That's a good point. Okay, so basically, if you want to understand what's going on, it's basically, we tend to think in symbolic terms. It's a very big discussion that's going on right now on the AI Twitter, for example, as to how much of intelligence is language. Just a second, I'll get there, okay? On one hand, clearly, language is the tip. But I would like to think of it as the battering tip of the intelligence. Because we have here not elephants, not mongooses, not even dolphins, that, you know, they have their own PR firms saying dolphins are the smartest creatures, etc. I don't see a single dolphin in the class. Okay, right? Why? Because we have language. How many of you have read, whether you like it or not, how many of you read Yuval Noah Harari's Sapiens? Shared imaginations. Shared imaginations. Every damn thing, government, religion, all of these are, we just share a bunch of things, more or less linguistically. Okay, and so our high-level thinking is very much in linguistic terms. And so you can argue both that you can't just do language and be intelligent. I agree. But you also have to admit that if humans are in the loop, they're likely to think first in terms of language. You see what I'm saying? So that's a very good distinction to keep in mind, because currently that's sort of forgotten. Yes, go ahead.
I was going to say how hard it is for AI to actually plan. So looking at the large language models, like they suck at planning. I looked at that paper and it's like they got the blocks world, they solved it like a couple times out of thousands. And I thought
yeah,
it was really interesting.
Except that honestly, we did so. The background of that paper is that it was a setup. I knew LLMs suck. You understand what I'm saying? Most of the time, I won't even bother showing it because everybody in the room would understand that. It's like saying, like a 2-year-old can plan, or a 1-year-old can plan. It's basically one of the things I remember, and I don't know how many of your parents here. Yes, okay, so one of the things, I had a kid, but he's no longer a kid now, he's like 26, but then I saw, and people having kids is sort of experiments in progress, sort of a thing. One of the things I remember is the idea of planning is essentially looking ahead. It's looking ahead and basically thinking about future, and then putting actions together, thinking about future. And that is a relatively late occurrence in development. You understand what I'm saying? So it's and what LLMs do are essentially tacit knowledge language generation. So it's not surprising to me that they won't do it. To the extent that people are surprised, that of tells you every time there is like the pendulum swings in a different direction. Right now, the pendulum has swung to the point where you think that unless proven otherwise, LLMs will be able to also, slice potatoes and make a good curry. Because unless you prove otherwise, they can do it. And the reality is, they should not be able to do a whole bunch of things. But it's well taken that that. Yes.
I guess one thing that I'm surprised about, it's still a little bit confusing. When you discussed emotion and task planning, I was, and I discussed this with another student, but I was confused as to why movement itself is separated from the actions that are outlined in task planning, because in my mind, movement itself is an action.
Yeah.
So it's a little strange to me. It's separated.
No, so actually that's a very useful thing. And you know that I said this before, but for the rest of the class, I want you for the entire semester here, think in the background about tacit versus explicit knowledge tasks. Or you could see this, or that one, okay. I don't know, yeah, that's true. Is that okay? Okay, I kind of assume that everybody has thought about it, but tacit knowledge tasks are things that we are able to do, but we don't know how we do it. We can't actually, one way of saying it is we can't write a nice little essay explaining how we do it. Explicit knowledge tasks are things that not only do we do it, but there are rules that we can actually articulate as to how things are done. Much of animal intelligence, and that includes us when we are very young. We are basically animals too. Just slightly, we have better certain kinds of facilities, better like such as linguistic facilities, but most animal intelligence is tacit knowledge. Okay, and it's extremely important. How do you walk? How do you hold this? How do you articulate sentences? Basically, kind of modifying your. Think about planning to speak by controlling your vocal cords. You just trip over and fall and die. Those are things that you do without thinking. Not only do you do them without thinking, even if you think you don't know how you do it. That's very important. Certain explicit knowledge tasks, first time around, you use the rules to figure out how to do them, and then after doing it many, many times, you just compile it down. You understand what I'm saying? At which point you are sort of doing it without thinking. But in those cases, it's like source code is there in the system 2, explicit knowledge, and it got compiled into system 1, which is tacit knowledge. Again, the tacit and explicit are sort of connected to system 1 and system 2, which is basically, as some of you know, it's just a hypothesis. There is no, if you actually do lobotomy, there won't be a place of the brain calling I'm system 1, I'm system 2. It's a kind of a metaphorical distinction. And system 2 is deliberative behavior. System 1 is reflexive tacit behavior. mostly system one contains tacit knowledge. The tacit knowledge may be compilation of explicit knowledge that used to reside in system two, or there never was a system. So the best way of thinking about it is if I just give you a binary versus I gave you source code and you compile it to binary. Because if I gave you source code that you compile it to binary, when you're debugging, you don't debug at the binary level, you debug at the source code level. Why? Because it's way easier. But if you only have binary, you're stuck with it. Okay, so the reason I'm basically bringing this up is things like motion planning are tacit knowledge tasks. Planning can be over tacit knowledge tasks as well as explicit knowledge tasks. Typically, tacit knowledge tasks don't have good models. Even if you learned the model, you are not aware of the model that you learned. You just do it.
Because of the nature of those tasks.
Exactly. So they're not linguistic in some sense. Whenever you do something, if you are able to give a linguistic description of the rules that you followed to do that, then that's it as explicit knowledge test. Otherwise, it's a tacit knowledge test. One of the interesting things is everything can be done as if it is a tacit knowledge test. Not surprising. Everything can be debugged as if it is just a binary program, even if the source code is there. But if you are doing it, you should slap yourself silly, because if the source code is there and you are unnecessarily only debugging at the binary level, you're wasting your time. Source code is a lot easier to understand, interpret, comprehensible. Do you see what I'm saying? So the interesting pendulum swing in AI has been that for the longest time, AI focused on explicit knowledge tasks. Whether it's planning or anything, explicit knowledge tasks. More recently, we got into tacit knowledge tasks. And one of way of thinking about this is that for the explicit knowledge tasks, actually, AI systems doing it can be the humans telling them how to do it, some steps of how to do it, and the AI systems doing the inference over it. That's what happens in planning. That's what happens in like rule-based systems and so on and so forth. AI systems doing vision doesn't work that way, because if I tell the vision system how to do vision, it would fail because I don't know how I do vision. I can't teach what I don't know. You see what I'm saying? Okay. So that for the tacit tasks, only learning approaches would ever work. Because that's the only thing. I mean, we just basically, sort of saw a whole bunch of program examples and somehow picked up, some model which is uninterpretable. We are not aware of it ourselves. Okay. That worked very well for vision. That also works for example, manipulation, etc. Those were the things that weren't considered back before, let's say, 2006, 2010 timeframe. Now these are working, so you tend to assume that everything is binary code. And of course, you can solve everything as a binary code debugging or a tacit knowledge task, but it could be quite inefficient for one thing. And secondly, it could actually be bad because humans in the loop would not have an understanding of what it is that machine. And in general, you have to understand that we ask for explanations, if you think about it, only for explicit knowledge tasks. You never, have any of you asked your friend, why did you think it's a dog? How many of you asked somebody, why did you think it's a dog? Nobody seems to ask. And yet, entire explainable machine learning is asking a machine learning system, why is it a dog? Why is it a cat? As if we can explain why it is a dog or why it's a cat. Do you understand what I'm saying? And why are we asking the system much? We don't ourselves ask those questions. Whereas when we ask for explanations, we ask explanations about things for which we have an understanding of, at least a partial understanding of how the task is supposed to be done. And then you want to understand what are your reasons for doing it this different way. Yes, yes.
But what if they get confused by like a cat and they think that it's a dog,
Mhm.
then we can ask them the question, right? Why do you think it was a cat?
No, so again, what I'm saying, the interesting part about vision is, in general, you have partial understanding of, there is no such thing as I have no understanding, I have full understanding of it. So explicit and tacit are the two extremes. Oftentimes, most interesting problems will have aspects of explicit, aspects of tacit. Much of vision is really tacit. A few things, like, for example, it's actually not very clear to me that if I were to give you two very close looking cat dog pictures, there would be a simple, rule that you can use to figure out which is a cat, which is a dog. By the way, grammar, English grammar is one of the crazy nonsensical things, right? Because it's part tacit, part explicit. And you will have a rule, and there will be an exception. There will be an exception to that exception. There will be an exception to the exception to the exception. And the interesting question is, after how many cascade of exceptions would you say it's just tacit? There is still an advantage to see if you know the structure. You can call everything binary. You can call everything tacit. What you lose by that is explainability, interpretability, efficiency, etc. Okay, so I will send you a little screed that I wrote that I think I made the fall 2021 folks read, but the rest of it can read. It's a CSEM 2-pager called Polanyi's Revenge and AI's new romance with tacit knowledge. A new romance because until 2006 we didn't do well in tacit knowledge. Now it's working. Now you see everything is tacit knowledge. Imagine there were no techniques for doing binary debugging. The only debugging that you could ever do is at the source level. And then one day some Adam Dupy kind of character said, hey, here are a couple of things that you can do at the binary level. And then there is this temptation to say everything is just binary. We'll just, if you have source code, throw it out of the window, take the binary and give it to Adam. Adam is a smart guy, but what you're doing is quite dumb. Right? Because you could do a lot more if you have the access to source. Think about these sorts of things, because again, this is a graduate level course, and I'm still hoping that you will do research in these areas. And so you have to be aware of, what are the trade-offs and so on. If there was any other question? Yes.
So this whole conversation of tacit versus explicit AI, I met somebody through the XP API at Facebook. So I was just talking to them and I said, I'm more interested in explicit AI and seeing how we can use that. And he said, it doesn't matter. He said, you can use tacit versus explicit, but use something that works for a specific case. But talking to lots of people, that noticed that tacit AI is what everyone's using, even though they don't need it. Like,
because it's again, as I said, by the way, I just made up, I should write it myself here. Adam Dupy example. I make up these things when talking to people. It's just because Adam cannot actually, Adam is a smart guy, but he can't do every possible binary debugging. He has a couple of tricks up his sleeve. Before you had 0, now you have 3. Now I think, that's good enough. I'll just throw all the source code out. That's kind of dumb. There may be a scenario where, and basically, first, because you won't actually be able to do everything. And secondly, whatever he's doing, that understanding, interpreting what's happening at the binary level is always going to be hard. Unless you are an expert who is going to spend time. Okay. And another thing, a related thing here is, I may have mentioned it last time. If a human is working a computer, I think I mentioned this last time. I think that the burden should be on the computer to make sense to the human, not vice versa. I know up until very, very recently, it was, like basically people doing computer programming had no other lives. And they will just go live in the computer. And so actually they probably wind up having no boyfriends and girlfriends because they actually talk to them as if they're computers too at some point. Okay? But part of AI's, thing is that it should make it easy for us to work in our natural modalities. See what I'm saying? And the natural modalities would not be lobotomizing other people. Natural modalities are basically they explaining themselves to us in the world. Yes.
So one example of mixed tacit and explicit be like a vision AI that categorizes things by taking little parts of it using tacit recognition.
Possible.
This is an ear, this is a wheel.
Yeah.
And then being like, okay.
That's
those
that's
together.
basically the kind of partial knowledge this gentleman was talking about. You know, to the extent there are rules differentiating cats and dogs. Actually, I don't know. If you ask me to write down, I don't know how to write. In fact, by the way, I always felt, I mean, I'm a bit of a, like, you know, there's somebody, when you're walking on the road and somebody mugs you, right? You go to the police station, they will say, describe the person. If you mug me, I will be extremely bad at describing it. Based on my description, they might write a cat picture. And I'm just very bad. My wife looks at somebody's face and she's able to see all these interesting distinctions. I look at a face and there's a face. It's not that I can't see the faces. I do see that you're all different, but I can't describe it. I'm particularly bad at describing tacit knowledge in linguistic terms. Here's a very interesting thing to remember in thinking about tacit explanation. A lot of, I mean, originally human civilization didn't have explicit knowledge of anything. Because to talk about explicit knowledge, you need to have language. And once we have language, we got so drunk with it that there are people writing 3 pages about how some particular pizza tastes. You can eat the damn pizza already. Because you can't describe how a pizza tastes. But we actually consider that to be a good thing, right? We basically pay people to write. They develop this jargon vocabulary about pizza description or even a face description. And there you are actually making up some explicit knowledge for what everybody does tacit. And they don't themselves know. So most of you eat pizza and I ask, how is the pizza? Oh, it's good. And it's very tasty. If you are a food critic, you can elaborate it into 3 pages. Convert it into some gobbledygook explicit knowledge description of how pizza is. The fact that we do this tells you how crazy we are about linguistic phenomena. Okay. Any other? Okay. So what we're going to do is this operator planning. Essentially, planning is synthesizing goal-directed behavior. And we are going to be looking at, and I already talked about the distinction between domain-independent and domain-specific planning last time. It becomes important today again because the planner, which is a computer program, doesn't care about which domain it is working on. It takes the domain as an input. That's what you will be doing. And the domain is described in a domain description language, which is PDDL, which is in our case, planning domain description language. And if you write the domain in the description, then the planner just runs with it. Okay, so PDL is the source code for a planner which actually knows how to run that source code. So we already talked about that. This basically is, yeah, you can see this. Yeah, now it's good. Okay. Okay. So you basically should remember that environments change, and depending on the difficulty of the environment, the planning problem would be hard. This is actually intelligent agents do action in the world. To do action, you need to have plans. Otherwise, you're just basically doing random actions. Okay. And so you should know the differences between deterministic versus stochastic, instantaneous versus derivative. That means is the action instantaneous or does it, right away execute? Observable versus partially observable. Discrete versus continuous. Is the state space discrete or is it a continuous state space? Static versus dynamic. Are there other agents? Or you are the only agent? And then, and to some extent, environment being observable, partially observable is kind of connected to your perceptual abilities. it could be that there's an environment that's perfectly, fully observable for you, but not to your visually challenged friend. Because it's not the environment, it is there. For them, the same environment is actually inaccessible. Okay, so that's why perception and environment observability are connected, as is the action type. So for example, even the stochastic, whether the environment is stochastic or deterministic, might also depend on the kind of actions you have. Some people actually can pick up things, very with guarantees and put them where they want. Other people who might have Parkinson's or some Parkinson's disease or thing, they kind of are basically stochastic in the sense they can't guarantee that when they pick it up, they will be able to put it right. Yes, go ahead.
In a multi-agent environment, is the ability to communicate perception a subcategory of perfect versus imperfect, or is
That's a very good point. I think that will happen to some extent. In fact, one of my jokes is, I think I mentioned last time, reinforcement learners die in a real world. Right? Because when you fall into like canyon, you die. Like if everybody is falling into the canyon and they're just dying, there won't be any humankind. The reason we figured this out is that we saw some of us falling. That doesn't look like a good thing. I learned something. Either you, while falling, you say, hey, I'm falling, don't come here. Which most of you won't do because you think if I'm falling, other people should fall too. Or I just saw you. I realized that doesn't look like a fun thing to do. I try to avoid getting it. Okay, so in fact, much of human knowledge is because we learn from each other. A lot.
So is that a subcategory about perception, the category perfect versus imperfect, or is it?
No, again, some of these things cross, but the world model that you have depends, that the world model that you're building is inside your mind is based on your own observations and experience as well as other people's experiences. So the distinction you're making is about the world model, not about this perception. Okay. And then, the full versus partial satisfaction is if I have a bunch of goals and I say that these goals must be done, that's full satisfaction. I give you a whole bunch of goals and say, do as many of the goals as possible. That's partial satisfaction. Which one is actually easier? Think about it. Which one is easier in life? Full satisfaction is easier than partial satisfaction. Do people understand that? So here is an interesting question. Solving the partial satisfaction problem. So actually what you said has to be qualified. The distinction between undergraduate and graduate's life, and in general life and undergraduate life, is undergraduate life is full satisfaction. We tell you, you must pass this course, this course, this course, this course, this course, and maybe one or two electives where you feel as if your choice. PhD, just do good research. Okay, so you could basically say, you can actually make your life very simple. A bunch of my PhD students are very happy because they say, yeah, I'm sure last day I'll do good research before the defense, the day before the defense. Right? And that would basically, so in general, partial satisfaction looks as if I'm giving you a choice. There are goals G1 to G100, do whatever you can. Be very afraid when somebody says, do whatever you can. Okay, because they act as you do. I just said it already in the class, I will grade it based on that. But you should be afraid because life is like that. Do whatever you can. But then if somebody else does better than you, we think they are better. Undergrad, everybody has to do the same courses. The maximum differentiation is the grades you get in them. That's it. Okay. Partial satisfaction, easier to live, but harder to impress in terms of performance metric optimization. Okay. For the full satisfaction problem, in some sense, optimization becomes easier because you have to achieve all those goals anyway. It's just a question of the cost of achieving those goals. For a partial satisfaction problem, I have a whole bunch of goals. I have to decide which subset of goals to work on, which depends on how hard is it to work on them. The only way to figure out how hard is to work on a goal is to work on them. This is crazy. But this is life. Okay. So anyway, those are all some of the distinctions in the environment that we talk about. Having said that, I will basically, the first thing we'll be talking about, I don't know, ignore that, is this classical plan, which is like the easiest case ever, which basically takes the easiest part of static world, deterministic world, observable world, instantaneous action, and the state is propositional. In fact, I can even make state the black box state. Okay. Actually, I think the distinction I'm making here is discrete versus discrete. Discrete versus continuous cases. Classical planning is discrete state space, instantaneous actions, fully observable world, deterministic actions, and you are the only one in the world. Okay, that's as easy as it gets. And we will talk about the fact that even in that case, for the simplest, domain description languages, coming up with a plan. By the way, somebody was saying earlier how hard it is to do something. One of the very interesting things that has been happening in AI is nobody cares about complexity. Okay. Why? Because you throw all the computation offline. 5 more GPUs. Right? You see what I'm saying? In fact, this is the time when you can go to the data structures class and say, screw it. It's okay to do sorting by looking n factorial permutations and see which is the best. Does anybody care? How much you spent beforehand? Only if you tell them. You understand what I'm saying? So in fact, I have, by the way, many of these things, if you remind me, I'll send you. There's like a tweet thread I did called Death of Complexity in AI. And it's basically a useful cultural phenomenon to keep in mind. Because as computer science people, you kind of know about complexity. You tend to think about, NP-hard and piece-based complete, or even undecidable. Somehow, the way the world works, nobody talks. When you're talking about, problems being solved in, certain types of deep learning systems, you don't tend to think in terms of what was the actual expected inference cost. Okay, and so you need to kind of ask those questions. The same people who ask questions about inference in the, like a symbolic paradigm, we just sort of ignore that cost. Partly because we essentially say offline doesn't count. Offline is not counted. So if you can spend, those of you who remember AlphaGo, right? AlphaGo, if you were trying to, at the time AlphaGo, 1 over least it all, if you try to get AlphaGo, like the code, try to train it on your, super dicey, good desktop, new desktop, a little GPU. In 1700 years, it would have been. And then you would have 1 over least it all because he and his friends as well as yourself would have died. You see what I'm saying? What they did was, they essentially put tons and tons and tons of compute power and said that doesn't count. All we care about is how much, whether or not we can win over this. Again, I'm not saying it's a wrong thing. Humans don't get to do it. Even if basically we don't tend to yell at a student who doesn't see any movies during the entire semester and studies for the course and gets an A+. You don't yell at them saying, how do you do it? Why should you do it? No, you should be given lower grade because you didn't have a life. No, we don't do that. Because life is finite. All of you have the same damn life. You chose to do some other things. You did this partial satisfaction, you said movie stuff is fun. And a couple of C minuses, nobody knows. right? But when you're doing it with GPUs, it's not finite. It's actually much more flexibility that you can use in terms of, if mind is doing it, it has a lot more resources. Even Demis Hassabis, maybe Elon Musk thinks he can live for more than 100 years. Those are enough. Think that. But Demis Hassabis is not going to live more than 100 years, plus or minus. But his computers can do what would take 1700 years right now on your GPUs. That changes. And you have to think about this, right? Because we never question human performers. Saying, no, yes, Kasparov won, but the guy never had any life. He was only playing chess. So we should let Rao get the prize. He only played chess before coming to this match, and he still kind of almost won. We don't do that. Right? But we do basically, in the case of computers, essentially we have all that extra time, so we may have to consider making apples and apples comparisons. Anyway, so that's the classical planning we're doing, and I'll talk about that mostly today. But I will say also that as you extend, other kinds of planning come. For example, if instead of instantaneous, you have actions in duration, that means each action doesn't get over instantaneously. It might take like 17 hours, or 3 hours, or 25 minutes. Then you're talking about temporal planning. Sure, I think real world is full of actions that have durations. You have talking about temporal planning. If you actually have instead of propositional, that means instead of discrete, you have numerical constraints. Then you are talking about essentially, a kind of planning which involves taking into account both discrete and continuous quantities together. Okay. In fact, in computer science, in general, continuous versus discrete optimization are different fields. Everybody and their brother now know about continuous optimization. Right? Okay. But a whole bunch of things that you did actually in computer science for discrete optimization. And people in operations research, who sit in industrial engineering, they have these programming problems, so dynamic programming, integer linear programming, quadratic programming, basically even, which are discrete. So variables can only take discrete values. You see what I'm saying? And the techniques that work for discrete are actually quite different from the techniques that work for continuous. So much so that actually some people, if you have like a hammer, you wish that everything is a nail. So people who are drunk with the fact that stochastic gradient descent works, quote unquote works, would say the problem with logic is it's not differentiable. Understand what I'm saying? Because the stochastic gradient to work, you need it to be a continuous function. Okay, and so you might just say that the reason my particular tool isn't working, my tool, which is gradient-based optimization, doesn't work for non-continuous quantities. So you could either actually look for other tools too, which actually exist, or you can say that's the problem with the problem. It should really have been continuous. Logic should have been continuous, and then it would have been fine. Okay. Anyway, so then you have, we actually originally first talk about discrete optimization in planning, and then get to things like continuous optimization, because you have numerical constraints. If you have observability, if you have other agents, then it becomes a dynamic world. You can tend to deal with it either by having policies or situated plans, or by replanning. You do something, and if it doesn't work, if you're still alive, you try to redo it. That's a way. Okay. If it's not observable, then it becomes partially observable. Then you have to search in the space of belief states, list of states. So if there are 100 states, then there would be 2 power 100 sets of states. Each such set would be a belief state. And you will wind up having to search in those belief states if you don't observe, you don't know which state you are. And things can get worse, and you can say that the belief states actually also put a distribution over which state is what, how likely. Then it really becomes confusing. Okay. Then if it's not deterministic, then everything else is fine. If it's not deterministic, then you can do contingent planning, conformant planning, or MDP style policies. Those are all the extensions for planning. But we mostly will be looking at this base case, some other shape for a while, to get better intuitions. Okay. Of course, since I did one at a time, I can also do multiple things at a time. So if I do both stochastic and partially observable, then it's POMDPs. Okay. And similarly, if I have both stochastic and durative, it is semi-Markov decision processes. And there's a name for each of them, but the point is things become harder as you wind up having more difficult environments. The best environment is this, and that in itself is actually quite tricky. So modeling deterministic planning problems are what we will do first. And so the simplest thing is I want to first start thinking in terms of atomic transition systems perspective. I'll just review this. Atomic transition system perspective is I have states which are black boxes, and actions take me from states to states. Actions are state transformers. Okay? If it is deterministic, an action has to be a function. That means when you do an action in a state, you get exactly one state. I mean, there's a special case where the action cannot be done in a state, which means it's undefined. That transition is undefined. But it's called a partial function. But you can say that when you try to do something and the actions preconditions are not satisfied, you can do it. You can think of it in one of two ways. One is the moment you try to do an action which is not doable, that means that preconditions are not satisfied, then everything becomes undefined. That means the world comes to an end. Okay. The other is you do the action, you try to do an action whose preconditions are not satisfied, you remain in the same state that you were in before. So for example, I try to lift this with my little finger. Because I think it's a pretty good strong little finger, I lifted it now. Do you see any difference? No. Actually, there's a difference. I mean, I'm feeling my little finger is hurting because I tried to lift it, but nothing happened to the table. The world didn't become undefined. You're still there. Interestingly, from a computational perspective, in the search, when you're looking for plans, if world becomes undefined if you do illegal things, this is easier search. Yeah, but I mean, that's a very detailed point. If you remember it, it might come off use at some point of time. So anyway, you have action system, basically actions going from states to states and their functions. And this is basically what you discussed in the context of, and then in the case of atomic states, you can also have non-deterministic or stochastic transitions. If you do non-deterministic or stochastic, then what you're saying is when you do an action in a state, you get a distribution of states, or you can get a set of states. Okay, it's worthwhile remembering the distinction between non-deterministic versus stochastic. Non-deterministic essentially means that when I do this action in the state S1, I'll get one of S3, S4, S7. That's it. I don't know with what probabilities. I only know that the resulting state is one of S3, S4, S7. Okay. Whereas stochastic means I'm saying not only am I saying that I get S3, S4, S7, but I'm also saying S3 with 0.3 probability, S4 with 0.6 probability, S7 with 0.1 probability. Which makes you realize that stochastic means more knowledge. Do you guys understand that? For something to be stochastic, you need the probability distribution. You can make up one, but that's not true. Right? I mean, like, for example, I can toss a coin and say, if I have a coin that you gave me, and you are a CD character, I have no idea whether you have a fair coin or not. And you say, I'm going to toss, what do you think is the problem? What will happen? All I can say is it will come either heads or tails. That's it. I mean, if you have a really CD coin, it might even stand on the side. Okay. Which is, I think the Indians know the Cholet coin business. But most people will think it's just either heads or tails. You say 0.5, 0.5 because you think everybody, basically, people don't make up coins just to toss them. They just take the coin that's available, and those are all fair coins, and so it's 0.5, 0.5. That's an extra assumption you're making about the coin. Up front, you only know it's non-deterministic. And in fact, this is where, if you don't know anything and you still want to use probabilities, then people say, pick a distribution with the highest entropy. Right? Because if you have a coin, it's either heads or tails, right? It's either heads or tails. And I need to put the probability mass between heads and tails. Okay, here is 100% probability for heads, 0 for tails. The other is, 60% for heads and 40 for tails. So 100, 0, 60, 40, 30, 70, 50, 50. These are all distributions over 2 variables. You know that 50-50 has the highest entropy, because in any other case, you are making more assumptions than you are allowed to make. Uniform distribution is picked if you don't know anything, because that is making the least assumptions about the process. If it is a discrete, variable with only 2 values or only k values, this uniform distribution is what you take. If it is a continuous distribution which goes from -infinity to +infinity, you can't pick a uniform distribution. And it actually turns out that using calculus of variations, you can show that the distribution with the highest entropy is the normal distribution. Which is why it's reasonable to assume, if nobody tells you that they have this random variable and they just say it takes values from between -infinity to +infinity. They don't tell you anything more. You can't say, yeah, I think it's 79.7577. That's like bosoness, because you put entire mass in just one point. You can't also say uniform because it's infinite range, so uniform distribution will be essentially close to 0 probability. Instead, you have something like a normal distribution. The reason I got into this is basically stochastic means more knowledge. If I tell you that I have this coin which I have screwed around with and it's 70 heads and 30 tails, I will take that because you gave me the knowledge. If you just say I have a coin, I should assume that basically I don't know anything about it. So either I assume that it's like I don't know the distribution at all, or I assume the distribution that has the highest entropy. Do people understand this? I mean, you always pick uniform distribution when you don't know. You always pick normal distribution when you don't know. Why do you do this? It's because it has the highest entropy, which is the only thing. If you don't know the knowledge, assuming it away is not going to change the world. Assuming it away can change the problems, your life, like a cat closing its eyes and saying, now the world has gone away. That doesn't make any sense. Yes.
So when you're working with partially observable groups and you have belief states, do your actions then become non-deterministic?
Yes. So basically, if you are so that's a very good point. So I wish one thing that I should figure out is how to add slides fast. Yeah. Okay. So yes, I'll write it here. So if you have a belief state, non-deterministic belief state, that means it's one of these 5 states. and I have a deterministic action A. Right? Then you again get a belief state. The only thing you can say is the cardinality of the belief state cannot be larger than the cardinality of the input belief state. Again, this is grad class, I get to do this. I can talk about introduction. I do it even for AI, but it certainly would like to. I mean, I'm more legal to do this in grad class. Okay. So if you have a belief state, right, and you have a deterministic action, that action at most will take every state here to one state here, some other state here. It may take more than one state to the same state, in which case the cardinality will reduce. It can never take a state to more than one state, because that would make it non-deterministic action. You guys see this?
Shouldn't the errors that you have to the states, the next set of states compound with each action?
No. First think about just the cardinality part. Okay. And the cardinality part actually tells you certain things that you do. I mean, I may have used this in the intro to AI example. I'll stop. I'll try not to apologize for repeating some analogies that I might have used 1 year back. So if some of you have heard this before, forgive me, but others, most of you would have heard. So if you woke up in the middle of the night in your friend's home that you have never been to, you need to find the bathroom and there's a power cut and you can't see anything. What do? Typically, you try to look for the wall, then follow the wall until there's a hole in the wall, and then assume that it leads to a bathroom, leads to a clothes closet, like a closet or something. The friend won't be very happy to know. But you are trying to essentially estimate your state, because you woke up, you have no idea where in the room you are and where everything else is in the room. You know where you are, but I mean, really knowing where you are in the world is not exactly helped by knowing that I'm here. I need to know what else is around me. I need to show the map. The normal problem in partial observability is you don't know the map, or you have a partial understanding of where you are in the map. So you do some deterministic actions to just reduce the positional uncertainty first. This is what is called state estimation, state filtering. You do actions to just reduce the uncertainty in your state. Now, once you realize that you're in the, in the wall, at the wall, you can follow the wall until you get to the which is the reason why there is this joke, which is a cruel joke, but Helen Keller herself repeated it. That Helen Keller is this historically very famous blind person who was risen to very great literary heights. How would Helen Keller's mother punish her if she's being very fluent? You put her in a cylindrical room. There are no corners, so it becomes harder to localize yourself. Okay. So yeah, belief states, you apply an action to a belief state, you get another belief state. If you apply a deterministic action, the belief state's cardinality only reduces. Remember the bomb in the toilet problem? Why did it work? Because it reduced the cardinality of the belief state. So you could be in either a state where you are in the bathroom with this package having bomb, or you are in the bathroom with this package not having bomb. There are two different states. You did a deterministic action, which is flush the damn thing. Then you got a state where this thing is flushed and you're safe. You see what I'm saying? So you reduce the uncertainty in the state by a single deterministic action. Okay. Anyway, those of you who are thinking about this, if you still have access to your old Russell and Darwin book, the first part, before it starts talking about the A-star search, it talks about all these issues of belief state representations, what happens when you are applying actions, even in the atomic level. Okay. So S is a set of states and A is a set of transitions. The transitions, you can typically represent the actions. If you are talking about discrete set of states, continuous is another problem. Mostly I'll talk about discrete. You can think of any action as a matrix. So you have, basically these are the states, A, B, C, D, E, F are the states, A, B, C, D, E, F are the states. And in each row, you will put a 1, means if there's a 1 here, what that means is if you were to do this action in state C, you will stay in state C. Whereas the one here means if you do an action in F, you will go to E. Now, this matrix representation is actually quite general. This is sort of the lowest level description, first principles description of an action. Right? If you want to describe actions that are stochastic, fine. Instead of zeros and ones, you put small positive decimal numbers, between 0 and 1, such that every row adds up to 1. See what I'm saying? Then you have a stochastic action. So at the lowest level, that's the difference. The difference between stochastic and deterministic is very little. In one case, it's all zeros and ones actions, zeros and ones matrix. The other case, it's a non-sparse matrix. And interestingly, most of us tend to think of the world that is stochastic as if it is deterministic to just get by the world. People are extremely bad by themselves without computers about dealing with state uncertainty in their thinking. So they try to jump to conclusions. You understand what I'm saying? And which is why when you use pronouns which won't, for example, give the gender of the person, it's not as easy. You need to get used to parsing it. Right? Because you tend to imagine the world. A snapshot of the world is fully defined. If I say they did it, then it could be more than one person. It could be one person of not unknown gender. I don't know if those of you who may have heard of this old story, or I can send it to you later. People tend to jump when they see a description, they tend to just jump and reduce the stochasticity. And half of the problems, half of the paradoxes come because of that. Because we're just very bad at dealing with this. That's why we need computers. That's why there are paradoxes, half of the paradoxes are in statistics, because we just are bad at dealing with it. Okay. So the connection about sparsity and determinism is that when you take what is a stochastic world and acting as if it is deterministic, you just sparsified the action matrix. It was a dense matrix, right? It had 0.1s and 0.003s everywhere. You started quantizing the heck out. You said everything above 0.5 becomes 1, everything below 0.5 becomes 0 or something like that. When you start doing it, you're basically sparsifying the matrix. We know that sparse matrices are easier to deal with. We also know that deterministic worlds are easier to deal with. There's some kind of connection there. Okay. Okay. So these kinds of models are called explicit state space models. Again, if you are into this world, then you can actually multiply two action matrices. You will get a new action matrix that would be A1, A2. If you have an A1 matrix, action A1 matrix, multiply it by action A2 matrix, you get the matrix for the composite action A1 followed by A2. You can do planning with, you can actually do whatever planning or any reasoning about the world's evolution in terms of this kind of reasoning. Okay. If you actually have deterministic actions, you don't even feel like writing them in the matrix. You essentially think of it as a graph, states with edges. between the states. And each edge corresponds to an action. And if you do that, then if I have a goal, then the goal would be some state that you need to reach. Is the initial state where you are, or some goal, and the goal will be some state you need to reach. Then planning becomes A-star search. And planning becomes graph search. And everything that you learned in the beginning of introduction to AI, blind and informed search and A-star search, for essentially solving deterministic planning problem in the atomic state space. Just say I did graph search, nobody is interested, I'm not doing here. Yeah, I'm doing deterministic planning problem in the atomic state search. Wow, that's very dumb. But that's what you're doing, essentially. Okay. In particular, basically, in fact, A-star search is not the only graph search. We actually looked at more than one engine into AI. Lots and lots of different ones are there, climbing, etc. are there. But A-star is a good canonical search to remember as the type of solutions that you use if you are in atomic search, atomic state space. Right? If you are actually looking at the stochastic actions, and you also take the opportunity to say there is no such thing as the goal is not a single state, but goal is a reward. That means as you pass through different states, you get different immediate rewards, and what you're trying to optimize is the sum aggregate sum of the rewards that you get, which is a huge generalization of the A-star search. That would be called the MDP model. MDP is still doing it in the atomic state space. You see what I'm saying? The states are still black boxes, and the actions in MDP as well as A-star search can be represented as these matrices. Those of you who remember MDPs, you know that it has this T function and the R function. T is the transition function. Transition function basically gives you these matrices. The R function gives you the reward you get at each of the states. Okay. So then, again, we'll get back to MDPs. Probably that's one thing that I might review because some of the intro to AIs don't necessarily do it. We did it we did more than we did, I guess, the one in fall 21. But I may do a little bit more of it when we get to it. But MDP is just a generalization where your actions are stochastic and the goals are also, instead of fully required satisfaction, you're saying partial satisfaction. Just because there's a reward doesn't mean you need to get it. The easiest policy for MDP is I'll sit where I am. That's a policy. Nobody can yell it. Whereas if it's a deterministic graph search, you are supposed to go from start to goal. You say, I sit at start, they'll slap you silly. It's not even valid, you bozo. Remember validity? It's not even valid because you're just sitting at start. How do you think you'll get to go? Whereas in MDP, there are rewards. Just because they're rewards, that doesn't mean you should take them. You decided, I've given it enough thought. Just sit in this state wherever I'm finding myself. That's my policy. My policy is whatever state I'm in, I'll stay in that state. And if you forcefully put me in a different state, I'll stay there. That's what kids who want to play truant do. The mom say, go to school. I say, please put me in the car. I'll stand near that. They say, they're pretty smart. They decided the rewards you decided for them are not their rewards at all. See what I'm saying? So they don't want to deal with it. So they just. So again, this is what I meant. Saying that I've solved it, so coming back to the fully satisfiable goals with full satisfaction as opposed to partial satisfaction, finding a valid plan, just a plan, is much easier if it is partial satisfaction. It's not at all easy for full satisfaction, which actually gets me to the second part of the graduate undergraduate thing. To be any kind of an undergraduate, it's hard. Because you don't get to say, I'm an undergraduate, you won't feel like taking any courses. They'll slap you silly. You can get a 0.0 GPA, but you still have to take the courses. You have to show up in classes. Grad students who are supposed to get Nobel Prizes can say, I feel like not doing anything. That's valid. It's valid. Because that's life is closer to life. And in life, you can say, I won't do anything. It's valid. That's what you have to remember. That optimizing with partial goals is much harder. That student life is hard because they could just have a sitting to try to figure out what's the best optimal policy. And when we figure it out, we'll execute it. Undergrads, we structured your life. You have no goals. We decided what your goals are. And you better do them step by step by step by step. You may feel happy, you may feel unhappy, but there is no such thing as optimizing undergraduate study. I mean, you think I optimized because my bozo friend got 3.97, I got 3.9789 GPA. Hey, in the grand scheme of things, those are not optimizations. See what I'm saying? Optimization is much harder for partial satisfaction. So it is harder for MDPs. Finding a valid plan is much harder for full satisfaction. So undergrad life is actually harder day to day. Because that's why undergrads have this pretty glum looking faces, whereas you never see grad students feeling unhappy. They'll only feel unhappy the day before the defense. Oh my God, what did I do all these 5 or 7 years? Undergrads, we don't let you do that. We don't say, yeah, you can take all these courses before you're done and you can figure out your own policy. No such thing. We tell you what to do. So you have glum faces. Your life is hard, but you're not optimizing any huge deal. Grad students get to optimize a huge deal, but since they have a choice, they can choose to optimize just sitting down. Okay, you sat down enough, 15 minutes. Right?
It's that you should have the neighbors work the other way around than I just did, because currently this is off, but the only way you can turn something on is if the neighbor to its right is already on. So you can't turn this on. So there's all those never miss. Exactly, that's why you can't turn the 5th one on.
Oh, all right, I'll just do that.
Yeah, so you just need to add the neighbors work both ways thing.
Let me just try it myself.
Okay.
And then I'll ask.
Okay, we'll slowly get started. Yeah, so that's like I think that the Cliff Skirt version of what I was overselling to you, that the full satisfaction goals versus partial satisfaction goals are like undergraduate versus graduate life. Okay. So if nothing else, at least you will understand my tweets if you take my class. Yeah, that's the other bigger one that you can look up about data complexity in AI. You know, generally goes on and on. Okay. Okay. Yeah. Okay. So I'm continuing along and maybe faster. So as I said, we'll talk a little bit more about MDPs later in the semester. But essentially, MDPs, what would be a single path in A star search will become a policy in MDPs. By the way, you can solve deterministic planning problems in the MDP framework. It is just unnecessary. It's inefficient. Because in essence, what you do if you are to solve deterministic planning problems in MDP framework is instead of finding a path from the initial state to the goal state, you will find all source path to the goal. You understand what I'm saying? If I give you a single goal, then there is a version of the graph search where it says for every node in the graph, find the shortest path from that node to the goal. And you do it all at once. If you do that, that's a policy, essentially. It was overkill because it is a deterministic thing. And if you know where your initial state is, you will never actually be out of the path that you are following. It is required for, it's more required for MDPs because they have stochastic as well as partial satisfaction goals. So in fact, if you wind up having a deterministic planning problem, but partial satisfaction goals, that means multiple goals and you get to pick any number. And then you're still trying to optimize, find the optimal. That's actually seen as an MDP problem. So this is like MDP would be the more general one, but you might as well want to do the special cases when they are actually more useful. Okay. Anyway, atomic transition systems view is what you get to hear in the intro to AI oftentimes, but it's kind of too first principle. Okay, and people don't necessarily think of actions as matrices. Okay, so they are a great conceptual tool, but it's sort of like understanding differentiation this way. That's the first principle understanding of differentiation, but it's oftentimes it's quite inefficient to go all the way down there. Okay. So in fact, it tends to be the case that you typically want to think of actions in a lifted or factored form. States in lifted or factored. These are all the names they use. Form. So instead of saying each state is a black box, you say each state has some state variables that take on different values. And actions change the state variable values. For those of you who came to this world from the machine learning world, you can think of wherever I said state variables, you can think of them as features. Each state is a set of features. The only difference is when I say state variables, I might probably be just thinking in terms of discrete Boolean state variables, and then start thinking as general case, more continuous scenarios and more multi-value scenarios. But really, what you're going to do is in the case of features, you don't say, they can be continuous valued features, they can be multi-valued categorical features, they can be Boolean valued categorical features. This is the terminology that you will remember when you're coming from ML side. From the logic planning side, you think in terms of propositions and state variables. From control theory side, also you think of propositions and state variables. Like I said, remember there are many sister disciplines: control theory, logic, and of course machine learning. They're all interested in the same problem, and they use slightly different terminologies. But when you think of a state being made up of features, then you are essentially saying state has structure. And the actions only change the features. It makes it easier to provide compact representations of the world model, which is actually important if you're especially thinking explicitly about the world model. If you're just learning it from scratch, then whether or not machines have learned interesting features is anybody's guess, because in the representation learning, essentially somewhere along the line, they're starting from pixels and they're learning some higher level thingies that you don't know what they are. You try to visualize them. There's no actual connection to what you think of as features. In the case of images, you don't even have very strong understanding of what should be the way to think of image in terms of features. But if it's actually like a picture of a world, it doesn't necessarily have to think of it in terms of objects. Although we are more increasingly, if you do things like scene graph extraction, that would give you some kind of a relational model of the picture. That would be the state in terms of predicates and the relation between objects. Okay, so what we're going to do is look in those kinds of terms, and in machine learning, you will start from the current machine learning. You will start from, you'll assume that I'm just given directly like a picture, and I'm trying to extract these objects and relations from that. Here, I would assume that I know the relations on the objects, and I'm focusing on the inference. And these objects and relations can be extracted if you have a scene graph extraction kind of a system, or may have been given by somebody who knows the domain. Okay, for now we'll focus on the inference. Okay. So states are modeled, at the lowest level. At the simplest level, we assume that the states are modeled in terms of binary state variables in the operator planning, and you will assume that the initial state is complete. That means it tells you the value of each of the state variables in the initial state. And you will assume that the goal state just gives certain values of the state variables that are preferred. So in a way, goal state in this kind of a representation actually corresponds to many complete states. Initial state corresponds to a single complete state. If you don't know where you are, if you have uncertainty, in the partial observability, then initial state itself will leave some state variables without values. Which then means that you could be in one of all the states where the rest of the state variables have those values. You see what I'm saying? And if I'm thinking in terms of Boolean state variables, if there are k state variables, there are 2 power k states. Right? Because if you have k state variables, you can give true false values, there are 2 power k states. If of the k state variables, m are missing, that means you don't know the values of m of them, where m is less than k. Then a state with initial state with m of the Boolean state variables saying unknown and the others having their actual true false values is not a complete state. It is actually 2 power m different states. You understand what I'm saying? If it's like one missing, one state variable, you don't know what its value is, it could be true, that's a complete state, it could be false, that's a different complete state. In the initial state, if there's uncertainty, that's a bad thing. In the goal state, there's uncertainty that's more flexible. Basically, you're saying, I don't really care about the rest of the state variable values. I want these state variables to have these values by the time you're done. It's actually psychological. If you think in terms of the way we provide goals, we do it that way. I'll say you should be here at 1 o'clock or 1:30. That's not a complete specification. I don't tell you the color of the shirt you should be wearing. I don't tell you what kind of shoes you should be wearing. I don't tell you all sorts of other things. As long as you satisfy that particular constraint that you are in the class at 1 o'clock, 1:30, the goal has been achieved. Whereas if you're trying to figure out where you are currently so that you can reach that goal, you need to know your full state. So that's why in the classical planning, initial state is complete, goal state is partial. Actions are modeled as state transformation functions. Okay, and what I do is, an action essentially changes values of certain state variables deterministically. Like, for example, in the simplest case, suppose I have a switch, right? And the switch can have state on or state off. That means the complete state. If it's all that matters in my world is this switch state, then switch is either on or off. And I might have 2 actions, switch on, switch off. Switch on works basically in the on state and leaves it as on. Switch off works in the on state and makes the switch off. You see what I'm saying? Okay, that's just changing that one state variable. So if in fact the switch configuration is one of the many other important state variables in your state, the switch on, switch off is only changing that state variable and nothing else. It's leaving the rest of it. And we tend to think of actions that way. So here is a simple example of a strange one-way rocket domain where there is a rocket on the Earth and there are two blocks, and you want to get both the blocks onto the moon. It's a toy code, obviously. And I'm describing the initial state in terms of these state variables, or I said relational relational predicates. And by the way, this is one place where the intro to AI background will help. You know that in logic, you have propositional logic, you have relational logic, you have first order logic. And we talked about the fact that predicate logic can be confined to propositional logic with exponential increase in size, right? Because if you have at AE, that's a predicate over objects A and E, you can make it into a single proposition called at dash A dash E. Right? And so if you in fact have at, which is a two-array variables x, y, and x can take n values, y can take m values, then there can be n times m at propositions. You see what I'm saying? You would like to think in the relational terms because that's much more natural. You want to think in terms of predicates and objects and relations. But you could always do the actual work in the propositional realm if you want. Right now, I'll talk in terms of relational terms, but you realize that relational representation is syntactic sugar in the sense of you can always compile it down. It's like we talk in terms of higher level languages, knowing that they all get compiled down to assembly language anyway. But it's still worthwhile that because the source code typically is more compact than assembly language. Okay. So I'm considering, the at predicate, the objects, block objects, and the object Earth, the object Moon, and that there's a rocket object too. And so I'm saying A is on the Earth, B is on Earth, rocket is on Earth. And then I want my final state to be that A is on Moon, B is on Moon, and A is not in the rocket, B is not in the rocket. The in proposition, in predicate basically captures whether the A is in the rocket or not in the rocket. You can actually make it in RB, in RA. Now, notice that this is kind of a language that I'm making. Okay. So if I were to tell you in English that I'm thinking in terms of two blocks, on Earth, and then there's a one-way rocket, and then need to go to the moon, and can you write like a problem specification that a planner can solve? You write like this, that would be a domain specification. Write this, will actually provide you a little language in which you can, define the objects, define the predicates, write in action in terms of its preconditions and effects. So the actions that I have in this case are load, unload, and slide. Load, basically each action will have preconditions and effects. Preconditions would be specific sub-configurations over the state variables. So if the state variables have those values, the action can be done. And in which case, then the action will complete and then it will give an effect. All the effect means is that it doctors the previous state such that that particular state variable that it's mentioning, if it was not true before, it will become true. Everything else is syntactic. So in O1 is basically, you can think of it as the proposition in dash O1. And if it was false before, it will be made true after the action. Okay, so load, to be loading into the rocket, the object should be in the same location as the rocket. And then you need to, and then after that, the object would be inside the rocket. Similarly, if you want to unload, then if you do in O1, then after unloading, it becomes not because in basically is a predicate that only talks about whether the object is in the rocket or not. And the fly is a lot more interesting, complicated action. Like the simplest one that we will look at next slide, it's a blocks world, doesn't have this much of a complexity, but I want you to realize that you can provide reasonably interesting action descriptions in this kind of a language. So to be able to fly, this is a one-way rocket, it can only fly if it is on Earth. And when it flies, it reaches moon. So if it is on Earth before, then you can do the fly action. Then it will reach moon. Then it reaches moon. Notice this funny thing, it no longer is on Earth. This actually you might think that, obviously if it's a moon, it can't be on Earth. But how do you know? It is possible that it's basically you assumed that these two variables at rocket, the position of the rocket is one place. That's what you're assuming in your domain. Okay. And you're making that clear to the planner. That if it's on the moon, then it's no longer on the Earth. This having to write this, you could argue that this is sort of reduces the flexibility for people because they have to remember to say the obvious things. Normally, when I say you be in the class, I don't have to tell you when you're in the class, you won't be at home. This is what I'm saying. But here is the interesting thing. The complaint I'm making is you're already assuming that the action descriptors are compact. And once you are compact, you want it to be as compact as possible. If on the other hand, I were to do everything as actions as matrices, you would have complaint because you are screwed anyway, because everything, these actions will be in terms of every snapshot of the world will be a different state. And the action should say, if you are in this snapshot of the world, what will be the new snapshot? And you can imagine that all of them are like serially numbered, S1 to S million. And then I just say that in this state, you will do this action, you will get this other state. And I'm saying the goal states are any of this subset of states. When I do it that way, you would say, it's like nobody ever says assembly language program is not compact enough. But they will have all these hang-ups over, I love this particular, high-level language as against this other high-level language. I like Python because it allows me to do this. I like Lisp because it allows me to do that. Assembly language, people just get through it. Understand what I'm saying? So it's like expectations game. So since I'm trying to say that action should be represented as compactly as possible, it is kind of a letdown that I had to say that when you are on moon, you're not on Earth. It looks like that should be comparable, that should be inferable. It is actually possible to infer it. There are ways of doing it where you will provide things called state axioms. Which might declare to the planner, in addition to the action descriptions, axioms such as, if you are in one place, you can't be in another place. If you are at X, for all X and Y, at X, for all X and Y, X not equal to Y, at X implies not at X, not at Y. You see what I'm saying? So that would be the axiom. For all X, Y, X not equal to Y, at X implies not at Y. If I say that, that's an axiom. This is what you basically implicitly have, which is why you thought, why do I have to be told that the rocket is no longer on Earth? And the interesting point is that is an extra piece of information about the domain, and the simplest case is to actually point that out. Okay, the strangest thing, even as I'm discussing this, is when people started doing this kind of representations of planning domains, all the battles were, why aren't you making it more compact? It's like the kind of battles you would have in higher level languages. Now nobody has that kind of a one if you're doing it as essentially actions as some huge learned neural network, which takes some state description and outputs some state description. Well, I don't need to worry at that point because anyway it's not supposed to make sense to me. That's why again, as I said, there are religious wars for higher level languages. There are no religious wars for assembly language. We just think we have to deal with it. You're sunk anyway. Yes.
Seems to be contextualized as properties of the
Yeah. I mean, in the sense that you basically you remove that axiom, then you are allowing something to be more than one place. If you are in the quantum world, where it's not a rocket, but it's the, what the Schrodinger's cat, it can be alive as well as dead. So you remove that axiom. Everything else works. Now, the beauty of this sort of a thing is it sort of becomes writing the domain models, the kind of properties you have is like writing good higher level programs. Things like modularity. If something changes about the domain, how much of the domain specification do you have to change? If you write it as axiom, then you just change that axiom. If you write it this way, then in essence, you have projected that axiom into every one of the effects. So in the grand spectrum of high level to low level, the axiom one is even more higher level because it's more modular. Then comes this, and at the other end is assembly language or the matrix representation of the actions in the black box space. Okay.
So can the term axiom be used interchangeably with the term constraint?
Yeah, you can. Yeah. The words constraints and axiom, they're all essentially really, it's actually a very good point. In the CSP or in general constraints literature, a constraint says what legal configurations a set of variables can take as their values. In fact, this particular axiom is a mutual exclusion constraint. You can only be in one place at a time. Okay. And the interesting difference is the axiom, this one is called a domain axiom, and these typically are supposed to hold only within the state. So going from one state to other, you only do it via actions. Once you change one variable in a state, the axioms will then change a bunch of other variables. Think in terms of like Excel spreadsheet where you change one particular, you yourself as an external action change one particular cell's value. And there are constraints between cells which then change a bunch of other cells' values. Right? I change one person's grades because that's an action I'm doing. Changing the grade they got on the homework. It changes the cell corresponding to the average as well as the standard deviation of the marks for the class on that particular assignment. Because there is an implicit, axiom about those, connecting those cells. Okay. So this is an interesting one. This one essentially says the point about the rocket thing is if the rocket goes, rocket will be on the moon, but how do you make sure that the blocks go with it? The blocks to go, the block should be in the moon, in the rocket. You could do one of the following things. You can say that I have an action which says a rocket with A in it is one action, rocket with B in it is another action, rocket with A and B in it is a third action, and rocket with none of them in it is the fourth action. If you do it that way, then each of these actions will have additional preconditions. Saying rocket with A and B in it will say A should be in it, B should be in it before action rocket goes on. You understand what I'm saying? But that would be kind of a very specialized kind of, a rocket. I mean, it is a strange enough rocket, but it's a very specialized kind of rocket, right? What you would like to do is the rocket will go whether people are in, the blocks are in it or not. Whether blocks will reach there depends on whether they were inside the rocket. It's the same thing. The buses are going, planes are going. I may not reach San Francisco because I'm not sitting in the San Francisco plane. unless I'm kind of a president of the country or something, they're not going to stop the San Francisco plane saying a rob hasn't started yet. Let's just wait. You see what I'm saying? So my being in San Francisco is a conditional effect. It's not a precondition for the plane to take off. It's a conditional effect. You should call it precondition because preconditions means that if the precondition is not satisfied, the action cannot be done. You understand that? Okay. Whereas conditional effects basically say, so this action will always be doable as long as rocket is on Earth. And if in fact X is inside the rocket, for every X that is inside the rocket, after this action, X will be on the moon and not on the Earth. That's conditional. Okay. Now, having said this, if I were to then write this down as black box states, that is completely specified states, and I number them, I can still write the transition system as matrices. It's just that writing it this way is more compact, much more compact. The second question is, if I write it more compactly, can I also do search more compact? Like searching for the plan, is it any easier? Like the reason you do higher level language, what is the reason we write higher level language programs? Is it because they're becoming more efficient? No, actually, in fact, it's because we know what we're writing. Right? So writing this kind of a domain model is actually more comprehensive. People understand what you're saying. If I give you a bunch of matrices with zeros and ones, and I say, is it okay? Is this like a Block's world? How do I know? I have a life, I can't actually figure out, whether 0 is missing here or 1 is missing there. Do you understand what I'm saying? Okay, so the representation, higher level representation, first is for comprehensibility. And the second interesting issue is, can it also be more efficient? It actually turns out that it can be more efficient. Unlike the higher level languages, to assembly language. So it's like a imperfect analogy. So we'll talk about how to do planning in terms of these kinds of actions. Of course, you can represent it this way. And then once you understand the representation, when you say do the planning, you say convert it into a full graph and do graph search. You can do that. That's actually what you do for higher level languages, right? Unless you have an interpreter, higher level language, whatever you write gets converted into binary and it gets executed. Whether you wrote it first in the binary or whether you wrote it in source and then converted into binary, it doesn't make any difference. However, actually, that's one way of dealing with any of these models. A better way is actually to think directly in terms of this representation, to say how to put plans together and write search algorithms in that level. And that's actually very useful. It's a lot more intuitive in terms of making sense of how to change the plans as well. So we'll talk about it. Yes.
So adding more axioms would probably make it more domain specific than domain independent.
No, I mean, no, it depends. You take, no, remember this is the input. Okay, you should represent, the input should represent your domain. Whether the planner is domain specific or domain independent has nothing to do with how complex the domain description is. Planner becomes domain specific. In the extreme case, you say the goal, actually you say, I have a problem and it says here's the solution. That's a domain specific plan. Because it only knows how to do one thing and it does it. So the domain specification as well as the goals were combined in. Do you understand what I'm saying? Whereas all we are saying is we are still doing domain independent planning. The planner is waiting for you to give the domain specification and your initial state of the goal state. Then it will start checking along.
It wouldn't specifying that the rocket only flies if it has the boxes, make it specific to that task.
No, it's that domain. That's your domain. What can I do? What I'm saying is that the planner itself would have taken, if you wrote your domain this way, that guy wrote a domain in a different way. The planner is not going to change because of the input of the domain. That's what makes it a domain independent. Okay. Planner, that is the search engine. Okay. So that's basically, in fact, it turns out this particular language that I have called ADL, Action Description Language, which also allows conditional effects and also allows this kind of fun syntax like for all X. I have to say that the for all there is our finite universes. So you can still compile the conditional effects, first of all, into a without the for all. That means you can actually put the X, you substitute all possible values of X and you'll get different conditional effects. Furthermore, I told you that if you don't like conditional effects, you can compile that down to just simple preconditions. How do you do that? You will say there is a one rocket action for A and B being inside, one rocket action for just A being inside and B not being inside, and so on and so forth. But if you want to provide it more compactly, using conditional effects is very useful. Yeah.
Is there an accepted way of combining when writing about a domain or a set of rules? So can we ground half of the variables and then not ground the others? And is it acceptable, or should we always?
No, that is during the search.
Okay.
When you are specifying, you specify like this.
So
what the planner does, it can decide to right away convert what you gave into like a graph search problem and solve it. Or it can decide to do it at this higher level. And there the differences would be ground planning versus lifted planning. But the description of the domain itself is something that you are controlling.
Right. So when we are representing it, is there an accepted way of writing it? Like, for example, here we are using X because we have two blocks. So it's easy to describe it that way. But there's only one rocket. So there's no point writing it with a variable and then saying for all that when there is only rocket. So then we are instead of.
So the kind of questions you're asking essentially are like best practices in writing higher level language programs. Syntactically correct higher level language programs. What is a syntactically correct C language program versus what are good ways of structuring C level C programs. And there is basically best practices of some kinds, the kind of things that you're mentioning. And in fact, the first project essentially asks you to write a couple of domain models. And then you can try writing the same domain in multiple different ways and click on the plan and see if it takes more time, less time, etc. In fact, you should try to do that. Okay, there is no such thing as, again, it's like, are there good ways of writing C programs versus not, right? I mean, that's basically just, the people who give you best practices, that's about it.
Right.
Okay, so that is basically more complicated word. The one that people typically normally look at is as like writing examples in the class is blocks, which is basically the thing that people use in planning, right? And so you have a bunch of blocks on a table, and you have a hand, and it picks. These are named blocks, and you basically can change their configurations. This hand can pick up one block, put it on another block, or put it on the table, or you can unstack a block from a block and put it on the table. And I give you a configuration, and you have to come up with. And I give you an initial state configuration where all the blocks are. I give you a description of the goal, which is obviously partial, because I might say I want A to be on top of B and B to be on top of C, and that's it. And you're trying to come up with a sequence of actions that basically will take you to that state. Okay, right? So if you are looking at this in the blocks world domain, if you're looking at this in the blocks world domain, yeah. So the state variables here are on table X, on XY, clear X, and empty, holding X. Okay, these are like, these are the state variables? That's what I decided. It's like you're telling me how you wrote a program, and I say, why did you call this variable this? You decided that variable. So the right metaphor is, what are the variables that you are using? What are the, predicates you are using? And typically, if you have tried to communicate with somebody else, your freedom in calling them any random thing reduces. The good practices of higher level language program writing kind of roll their eyes if you write programs with variables V001, V002, V003. the program will run exactly as expected. And you know what those 0001s are supposed to be. But anybody else trying to read your program has no clue what's going on. You see what I'm saying? Because you want to communicate. That's why you write the variables in such a way that people make sense of the names. But as far as I'm concerned, I'm using these. Under the computer, under the hood, the computer basically thinks of them as just state variables. Okay, initial state is a complete specification, goal state is a partial specification. I'm going to look at this very strange problem because I like it. Where initial state is A is on table, B is on table, A is clear, B is clear, hand is empty. My goal is to have hand empty, but B should not be clear. Now notice this is where, remember I was telling you last class, if you ask AlphaGo, which is supposedly the world Go champion, that now can you please redefine the game goal to be putting, the pieces, whatever they call the stones, I guess, in such a way that you'll tell, hi mom. It's actually much simpler than actually playing Go, but it will fail. When I said blocks world, you wouldn't have thought of this as a reasonable goal. When you would think normally blocks world means you build big stacks. And as your kid, you kind of put on top of each other until it is the size of the Empire State Building, Empire State Building, and it falls down, right? But this is a goal. I get to ask this goal. That's the flexibility of domain independent plan. First of all, do people understand how to solve this problem? What? So if there's nothing on top of a block, then the block is clear. If something is on top of the block, then the block is not clear. That's the English meaning. We have to write the actions, and in fact, if you notice that the actions are written with that semantics in mind. Pickup X basically assumes that hand is empty, X is clear because you want to hold the block X, and X is on table. Pickup only works if X is on table. And then it gives the effect holding X. Once you pick it up, you're holding the X. And once you're holding X, it's no longer on table because it's only one position. And hand is no longer empty because you're holding something. You can't hold two things at the same time. And X is not clear. That's the way definition is. So X is clear only if it's actually sitting somewhere and there's nobody on top of it. And then put down is the opposite of it. You're holding something, you put it down. And stack XY is basically, pickup. It's actually pickup is like unstack. Unstack XY is doing pickup action on X, except when X is not on table, but it's on top of another block. Presumably, you differentiate both of them because picking up something which is on the table, you can use a cheaper action, whereas if it's on a block, you should be more careful. It could be on top of a long stack of blocks, and you need to be a lot more careful in picking it up. Presumably. Okay, and so then basically that's on stack, and then this is the stack one, which is actually put down when you're putting it on not on the table but on another. Okay, and so those are actions. First of all, I can also mention that you could try to write blocks world in a very different way. You can write it using just one action, move X from Y to Z. And you can write a description for that action yourself. Those are two different ways of writing the same domain. Okay. So one of the funny things is these would be called two representations for the same domain. Semantically, they are the same, okay, but syntactically their action names are different, etc., etc. And people used to talk about which representations are better, thinking the humans are deciding the representations. Now, when we talk about representation in deep learning, it's just it learns some representation. You don't know what it is. It knows. It doesn't know necessarily. In fact, by the way, I should mention that The tacit was like, there was a question in the middle of the class, in the break. I want to bring this up to the wider class. The tacit versus explicit is a big difference for humans. It's not for machines. Because unless you are Lemoyne and you take too long with lambda, where I'm going with this. Machines are not conscious. There is no such thing as I know what's going on. For us, there is a difference between walking where I don't know exactly how I'm walking, but I'm walking, versus stacking blocks where I know exactly what I'm doing. In one case, we can talk to each other about, this is the right way to stack blocks. And very rarely do I tell you this is the right way to walk. I actually just show you a demonstration at best. And then I hope that you might. In fact, most tacit knowledge tasks, people just pick it up from examples. I never taught my kid how to walk. I think that's why he doesn't walk as well, but I don't know how to teach him. He just saw people and then he was not predisposed to kind of stand up and start walking. Okay, so the point is, people can differentiate between I'm doing versus I know I'm doing, how I am doing. Machines just, actually there is no such distinction. When we are doing things in an explicit knowledge task, the way we are doing it can actually make sense to other people. You can actually provide explanations in that same language. If what is an explicit knowledge task for you is being done as a tacit representation task by the machine, and it tries to provide explanation in the learned representation that it has, it doesn't have to make any sense to you. So it needs to convert whatever it is doing into language you can understand. For walking, you would not ask it any questions because you don't know yourself how to walk. Okay. Anyway, so there are two different representations, but I won't talk about it right now. But look at this particular problem: initial state and goal state. Now, do people see that you can solve this problem? Give me an answer. What is an example? What?
Solution.
Solution.
Pick up A followed by stack A comma B.
Yeah. So pick up A followed by stack A comma B. It's a strange plan to ask a Bloxworld problem to Bloxworld planner to do. Almost as strange as asking a Go player to put the stones in high bomb configuration. But you can do it. The fact that you can do it is basically the point. You can do the other stuff too, but you can do even this. Okay, this is like putting on the refrigerator to warm the room. Have you ever done this? Right? Because actually, I have, the point is that when you put on the refrigerator, essentially it cools what's inside, but it also warms the outside. If you are stuck in a, there was a, what's the TV show, MacGyver? This is MacGyver planning. You see what I'm saying? It's a planning. It's not the kind of planning that you do. That's why, the normal planning, they don't make TV shows. MacGyver planning, they make TV shows because it is doable. Once they do it, you say, it makes sense. Right? But it's not at all the standard use for those things. Using a refrigerator to heat up the room is a non-standard use of doing it. But if you're out of all the things, that's what you do. I am watching Gray Man where that guy pours water into that bowl so that he can lift himself up. How he does it, yeah, that makes sense. But I never said for a neural network that, yeah, that makes sense necessarily. No, basically, right? So it's like you can understand how this thing is going on. Okay. Anyway, so that's the problem. Then you can write, there is an editor, there is an actual representation language called PDDL. I don't want to print the syntax, but this is the homework that I'll provide you that you can play with. You can write any domain once that you have an idea of the domain. If I give you some English description, you should be able to convert it to PDL representation. Not all domains, there are some explicitness restrictions, but mostly things can be done. For example, out of the box, PDL assumes Boolean variables. It doesn't assume continuous quantities. So if you have continuous quantities, then language is not useful. But there are extensions of PDL which have continuous quantities. Okay. So the basic PDL basically, looks some, it's kind of a, at one time we used to love this. I still love this, but so we write everything as a description. Nowadays, if you want to do PDL now, you write in the Python syntax because that's become the thing. Okay. So everything is, in humongous number of parentheses, and PDL there's some PDL specification for the predicate names, for the action names, and for each action there are preconditions and efforts. And so here are some examples. So suppose you have a gripper where there's a movement operator. A robot can move an object X from robot itself can move from location X to location Y. The precondition is that the X and Y are rooms because robot can only be in rooms, and then the robot is in X, and the effect is that the robot goes to Y, and then at that point it's no longer at X. I have to say that, and then in PDL you write it. It's just syntax. Okay, and then there are ways of writing. So once you specify this, that's the homework one that I'll make you do. It's a very simple thing, as I said. It asks you to play with some domains. It will give some English description of the domains, and you convert it into PDL representation. And then you can do this in a given editor, a PDL editor. And then that PDL editor also has somewhere, I don't know where it is, like I think is one of these places. It actually, you can click and it'll do the plan. There's an inbuilt planner, although it also takes your own planner into consideration. Okay, and then if it's a small enough domain, you can actually debug. If there is no plan, then you must have forgotten some precondition. And if you have a plan that's not going to work according to your English understanding, then you must have written the domain. Okay, so in the little homework that you're going to do, there are like a switch on and off kind of a domain that's very simple, and then there's a little more interesting logistics domain where things are going from place X to place Y, multiple trucks are shifting back and forth. And you get to specify the initial state, specify the goal state, and write the actions. Okay, and you have some independence in figuring out what actions are, what the names of the predicates are, although some cases we give predicate names, but you don't, can also use those. Even if the predicate names are given, for example, the difference between move XYZ formulation and stack on stack formulation of blocks world, it still uses the same exact predicates. It just uses different action formalizations. Okay. Okay. Why is more compact? Why is this more compact than explicit transition systems? There's a long description there, but essentially it's because you are saying that the action only has to specify what state variables change. In the atomic description, all actions are equal sized. Each of them is a matrix of size S by S, where S is the number of states. In this description, an action which only changes a few variables will have very compact representation. You know what I'm saying? Right. So the structure is being used. The representation uses the structure of the dynamics of the domain in terms of the state variables. So this is what we're saying. Consider a state space of 1024 states. It can be represented in terms of 10 state variables. Right? Because if you have Boolean 10 state variables, then we'll essentially log 1024 to the base 2 is 10. Right? So, and then you can write actions in terms of just those state variables on the Now, the big thing to understand is these work, and you kind of agree these work because you tend to think of the world like this. You tend to think of the world as actions with preconditions and effects, and there's only few preconditions and only few effects. Well, first order of approximation. But in the worst case, actually, an action might have many conditionalities. By the time you write all the conditionalities in your expressions, it becomes 8 pages long, and you will say, to heck with it, I might as well write an S by S matrix. What I'm saying is there could be times when I'm making you write a program, which is essentially there is no simple, compact, higher level language description of this piece of assembly language code. Writing it sometimes can actually be longer than the assembly language. It's the most pathological case, but I can make it happen. You see what I'm saying? The reason higher level language works is because most of the time what you want to say can be said a lot more compactly in that language. And it will then get expanded into compiler, compiler expands it into a whole bunch of assembly language. Okay, so that's the point that you have to understand as to why these are called the factored representations systems. Why are they more compact? Part of it. And one other thing is I want to say this, which is the other big reason is when I said actions are matrices, you understood it, but it wasn't obvious at all. That's the best way to think about it. When I said actions have preconditions and effects, I didn't hear people saying, what do you mean actions have preconditions and effects? Because you tend to think of the world like this. So there is actually support from psychology literature that naive world models that people use are in precondition effect form. So if you actually think in this form, people are likely to understand better, and people are likely to write them better. The reason higher level languages are more popular is because people are finding it's easier to write programs in higher level language. When I come up with a really bad higher level language, which is actually harder to write programs in than writing it in assembly, you'll give up on it. Same for the action representation. Okay, so this is important because this corresponds to something that I said last class, which is even if in fact, after I give you the description, you convert everything into low level, matrix representation, and you did some direct search there. If I ask you a question as to why is this action here, your answer is going to be better be in terms of the preconditions and effects that I asked. And that's where I'm learning. So imagine the debuggers, there is this word, a symbolic debugger. I don't even know whether they're using that word, but when originally, debugging systems came along, C, etc. Originally, there was really only binary debugging that people just tried to do, and then they started writing symbolic debuggers. People like symbolic debuggers because the messages are with respect to what might be wrong in your higher level language. And that's so much simpler for you to change. Now, if I actually did not give this domain, in this case, I'm saying I gave the domain model in the higher level language, the planner reasoned with it in a lower level compiled form, but then it's giving explanation back to me in the symbolic level. But change it. Now, suppose the thing actually just looked at humongous number of snapshots, pictures of the world configuration X and Y, Z, different configurations with the actions, and try to learn from that its own representation of the domain model. And it's able to solve the problems. The thing that is common between the you and them, the planner and you, is the action names. But it's looking at the states and the preconditions and everything, they're very, very different. If I ask it, why did you do this decision? It's not as simple to go back to the source code because there was no source code that got compiled down. Did you understand what I just said? That's where I would say you make source code. You provide explanation in a local symbolic model around that decision. because people understand it that way. This was a paper that I was talking about that we'll talk about here. I think Mudit was one of the authors in iClair this year, for example, where you let the system learn its own domain model, but when it gives an explanation, it gives it in these kinds of preconditions. That's basically saying, even if in fact you only have the binary and no source code, you're trying to help debugging by converting the problem is the binary into some kind of higher level language. Okay. Okay. Okay, so some notes on action representation. Okay, some notes on action representation. Some things that I already mentioned. So this representation, even though we call it PDDL now, it's also been known as STRIPS representation. And the word STRIPS stands for Stanford Research Institute Planning System. Why is it Stanford Research Institute Planning System? If I go forward. Like that, like shaky. That's the history's first robot that could make its own plans. It can give it higher level commands, such as to put these blocks on these blocks, and it will, try to make a task level plan, move to the blocks and put them in that form. It was called shaky because when it was moving, it was shaking like a Parkinsonian robot. Okay. And when the project was done, 1969-70 time frame, they had to come up with a description for writing the problem description, and they came up with this STRIPS action representation. That's why we call it STRIPS action. Well, actually, the way the search is done by STRIPS planner is quite different. I mean, that's a different part. I mean, trying to solve the planning problem, first you have to talk about how do you specify, the other is how do you search for the solution. STRIPS package both into because it's the history's first planner. Actually, if you get a chance, and maybe one of us remember, I should try to send you the Artificial Intelligence Journal paper on STRIPS. So the nice thing about that is that basically those are the days where as part of the problem, part of the paper, they could also write the code. Because these are like the early days of computer science. And look, I wrote code. So these people, essentially, as part of the paper, there's actually a whole bunch of the code for STRIPS. That's just part of the paper, not appendix, not on GitHub. There was no GitHub. That's fun days. In fact, Shaky is so influential that 72 plus 50, 2012, basically, we had a 50th anniversary celebration of Shaky in India. If you remind me, I'll send you pictures from that, with Bill Nilsson, who was the guy, Elsa Sedoti, and all these people who were involved in that project. It was like a pretty big, influential project at that time, and the name STRIPS comes from that. Okay. Okay. So also there is something called STRIPS assumption. And the STRIPS assumption is the shorthand name for saying that the effects, that action should specify every state variable value that will change after the action. Which basically means STRIPS assumption says there are no domain axioms. Because if there are domain axioms, then you will just change a state variable value, and domain axioms change some more state variable values because of that. Saying, for example, that rocket is on moon and also saying it's not on Earth is STRIPS assumption. It makes me do it. If it makes me do it, then I can make certain kind. Basically, then the search becomes much simpler. Search for plans becomes much simpler. There's no theorem proving in between. Because domain axioms are there, then you need to do some extra theorem proving to see what else actually becomes true. Otherwise, we just essentially are changing state variables. It's like algebra. You put an action, if the preconditions are true, then it changes the state variables, you get a new state, and then you go on until you reach the first. Yes.
Can the changed values in the strip assumption be probabilistic changes? Or are they all?
No, strips is the simplest case. There are variations, just like MDPs have variations, strips have variations. You can have probabilistic strips, you can have curative strips, etc. But this is the simplest case. Okay. And it's worthwhile understanding that because in many cases, you can either compile the complex one to strips, or you can understand at least what, if you understand what's going on there, much of my arguments that you should have a symbolic understanding of what's going on would basically work out just with the strips assumption.
So this is the abstraction.
No, but this is also the simplest abstraction. Okay. And understanding how planning works there helps you in understanding how planning works for this, slightly more complex models. Okay. So as I said, no disjunction allowed in FX because of deterministic actions. There's disjunction, that means there's stochastic action. So probabilistic strips, for example, will say when you do this action, it changes this state variable with 0.7 probability, and this state variable is 0.3 probability. Okay. So this is the simplest case, and then conditional effects are not disjunctive. This is actually a very useful thing to understand. Again, sometimes you know more, you get confused more. Kids are not confused at all if they don't understand anything. Looks fine. Okay. So one of the interesting questions is I said there is no conditional effects. And I also said I can have an action O1 which says the conditional effect, if A is true, then B is true. And you might think, using your background in logic, you will say, well, A plus B is nothing but not A or B. Now is wrong because it allows conditional effect. Conditional effect is disjunction. You said no disjunction. Why is this not a problem? Because A and B are in different states. Conditional effect is not a logical axiom. It uses logic syntax, but it's not a logical axiom. Because it says if A were true before the action, B will be true after the action. Whereas a disjunctive effect is saying after action A is done, in the remaining state, in the resulting state, A will be true with either 0.5, 0.7 probability and false with 0.3 probability. That I wrote down. You understand what I'm saying? If I didn't say this, you wouldn't have thought it's even a problem. But I want you to realize that this is a confusion that can happen as you understand more. And it's not a confusion. It should be confusion because it's not wrong. There's no paradox here because conditional effects are actually about two different instances of the word. Okay. Quantification is there, but normal strips, normal strips doesn't even allow quantification. Normal strips also doesn't allow conditional effects. Conditional effects is an extension of strips. But as I said, conditional effects can be compiled. That would be rocket with A and B in it. Rocket with only A in it. Those are all the different actions. Similarly, quantification is an extra extension on the strips, but the quantification is over finite universes. So it also can be compiled. It's not surprising. Much of higher level languages is syntactic sugaring because they ultimately are compiled down to finite sized assembly language. If it becomes infinite size assembly language program, you have to pick up. Okay. So that's that to remember. And then all actions can be compiled down to a canonical strips representation. But it might mean exponential blow up, and it also might mean that people understand the higher level specification better than the compiled. There are two different issues in all these cases. One is interpretability. Is it easier to understand the higher level representation or the lower level representation? The other is it more efficient to reason with the higher level representation or the lower level representation? Those are not one and the same. Do you understand what I'm saying? So let me actually write that down. So, yeah, I can write down here either two. is it easier to understand, to interpret? Representation 1 versus representation 2. Second is it more efficient to reason with R1 versus, and these are not equal, they are not correlated necessarily. Okay, and in fact, I'm allowing that. In fact, I'm allowing in that ICLAIR paper that I was mentioning, I'm allowing the machine to not even use strip representation. It uses some random representation that it's using. It uses the same actions I'm using. And it needs to explain to me, and it needs to take advice from me about my problem specification in the words that I understand. Okay. And then, this is the whole thing about plus and cons of compiling it to canonical representation. I think I kind of explained it to you. You can read it again, but in general, you compiling it down, interpretability might reduce because there's like one conditional effect action has become exponentially number of simple strips actions. So the question about compiling conditional effects is, do you prefer to have a rocket which just goes whether or not there are blocks in it, and if the blocks in it, they will actually get to moon? Or would you like to make a different rocket action for each configuration of blocks? Clearly, it's very unnatural to have many exponential number of rocket actions. That's like having exponential number of plane actions. Plane takes off with some subset of people in the world. For each subset, it's a different plane takeoff. Makes no sense. Okay. Okay. I'm going to skip over those blocks world, and actually what I want to do is how do we do planning, and I'll get back to this, I guess, when we come back. But really, I really believe that I can do this and complete the class-based planning. So how do you do planning? If we have this kind of representation of state variables, etc., how do you do planning? The best way to think about it is this, which is my general idea, and this is actually coming from programming, that if you're trying to look for a solution, you're going to search for a solution. The first question you ask yourself is, if the solution comes and bites you, can you recognize it? You understand what I'm saying? So I'm trying to find a sorted sequence. If I give you a sequence, can you tell it is sorted or not? How do you prove that a sequence is sorted? And finding a sorted sequence is inverting the truth. That's a great way of thinking about programming in general. If you know the invariant about the solution, the search is inverting that proof. You understand that? So now the question is, in this kind of representation, ultimately plans would be sequence of actions. Right? You're looking for one. I come and say, okay, here's the sequence of actions. Can you tell whether it is a solution or not? If you can't, then you should waste your time trying to look for the plan yourself, because if you don't know how the solution looks like, what are you searching for? The way you can tell whether it's a solution or not is by proving it to yourself that it's a valid plan. You see what I'm saying? Now it turns out that the simplest way you convince yourself that something is a valid plan is start from the initial state, do the first action, you'll get the new state, do the second action, you'll get the new state, and then until all the actions are over, look at the final state and check if the goal propositions have the values that the goals want. Then you're done. Agreed? That's called the forward or the progression proof. Okay? You invert that, you get the progression search. Essentially, you start from the initial state, You apply actions in different branches, you keep expanding these branches until it reaches, one of the branches reaches a state where all the goals are there in the state. You think that's the only way, but every different way you can prove that something is a solution gives rise to a different kind of a search. The second one, which is little unintuitive, so this is progression search. Progression proof. So progression proof inverted becomes progression search. It's the most obvious one that you can ask. A different way is regression proof. I give the plan. You prove to yourself it's a plan by checking, for example, if I take the goals that I want, regress them on the last action, I'll get some more sub goals. Regress them on the next action, I'll get some more sub goals. All the way until the first action, I'll get a bunch of sub goals. If all those sub goals are already true in the initial state, I'm done. Yeah.
Wouldn't you need opposite actions to be defined?
No. This essentially, the regression is you don't need to change the action description. You are just reasoning. I'll tell you in a minute. So for example, so the way to describe regression. So this is the progression description. I actually, you can look at it. I'll mention it next time again, but it's pretty simple, obvious. Regression is more interesting. I'll talk a little more about it next time, but essentially it says if you are trying to regress a fact P over an action A, first thing you check is if the action A has an effect not P. If it has an effect not P, then P can't be true after this action. Right? If as long as it doesn't have the effect not P, then you ask another useful question. Does the action give P? If it does give P, then you will assume that this action will give P, and then I just need to make the action executable. That means I need to take all the preconditions of the action and say that's the next step. This is actually how people prove correctness of programs. That's one way of proving correctness of the plans. And the one guy is crazy about this here. Plans and programs are very similar. Plans are much simpler than full-on programs. But the way you prove the correctness of a plan, a program, is you compute the weakest preconditions for program to execute successfully and convince yourself that those weakest preconditions are actually holding in the input specification. That's how you prove the correctness. That's what you're doing here for regression. I'll go into a little more detail about it next time, but I want to tell you one other crazier way to prove before I let you go. So I can prove the plan to be correct by progressing through the actions. That will give me a progression search. I can prove it by proving that regress the goal state through all the actions, I'll reach the initial state. That means the weakest preconditions are satisfied in the initial state. That will require search in the backward direction. So where actions are applied in the reverse way, you don't change the actions, you just apply them in the reverse way. Okay. A third one is really even more interesting, actually, which is you say plan is correct because for every top level goal, there is a contributor. Some action says, I am giving that condition. And after they say, I am giving that condition, nobody who comes after them deletes that condition. So I would say that for every top level goal, there should be a contributor such that nobody who comes after that contributor will kill that condition. Now, anytime there is an action in the plan, it has preconditions. Goals are just the preconditions of the end of the world action. Preconditions of the actions themselves are just sub-goals. That's what you did in the regression too. right? So you require that for every given a plan, consider the set of all the top level goals. Think of that the very end of the plan as action infinity, which takes the goals as the preconditions and says done. The plan is done. My proof says for every precondition of every action in the plan, there is some action that precedes it, that has an effect that gives that condition, and no other action that comes in between deletes that precondition, deletes that condition. If you do this, and if it, that means basically a way of thinking about it is that there is, the terminology is, there is a causal link. There is an action that is causing this condition to be true. And once it causes that condition to be true, you are protecting it from this action all the way to where it is needed. That means there is nobody else coming in between that is violating that condition. How do actions violate conditions? They have an effect that is offending. In the regression, remember, we can't regress P over an action which has an effect not P, because that's the last thing you do. And after that, you get not P. Like, for example, I want to be alive. The last action should not be, I will jump into Grand Canyon. It's very obvious. When you jump into Grand Canyon, you die. You want to be alive, you shouldn't do it. That's the last action. Okay. So all I'm saying is for every condition, there should be a causal link, and the causal link should be protected. This is a crazier proof, but it actually makes a lot of sense. You tend to think of plans in your life this way. You neither think of it in the progression way, nor think of it in the regression way. You tend to think of, oh, I have a whole bunch of things. Oh, I need to go to San Francisco. Have I yet bought the ticket? Yeah, I bought the ticket. Have I lost the ticket? No, I haven't yet lost the ticket. So that part is fine. For everything I need to do, I know somebody is giving it and nobody is deleting it. Then I'm fine. This is actually how you think of plans. It turns out that you can actually, give me 2 more seconds, 1 more minute, 2 more minutes. I just want to show you this slide. I won't go through it, but you can actually do search by inverting this proof. And in fact, there is a slide there which tells you, takes you through the steps of it. You know, I kind of, I feel sad because I did all this thinking I'll complete this work today, but there is. Okay, I'll get back to it next week. But you can search by undoing, with inverting the causal proof. If you do that, you get causal link plan. You have at least 3 different ways, each corresponding to one particular way of proving that the plan is. And they have very interesting properties. They, not always, they're not all equally good, but they have relative advantages. And it's worthwhile understanding, because sometimes when you think, the one thing good about causal link planning is that the proof is local. You can actually disprove that a plan won't work by just picking one condition that you need and say, look, you're not going to San Francisco, my friend, because you need the cabs to be running, and I've shown that the cabs won't be running that day. Done. I don't need to do major progression or major regression. I failed one precondition that your plan requires, and I have proved that the plan won't work. You see what I'm saying? We'll get back to this. No, that's so the model. So the actions in the plan, the effect of those models, that particular action, according to your model, an action that is coming between the contributor and the consumer and violates the condition. And if it's not modeled, that means this action actually has a negative effect, but you please model it. Then The plan is still valid according to your model, you know, but it just don't work in the
Yeah.